Example 4.13 is going to give us a lot of really good insight into what the derivative will mean for a function, and it's going to apply it to a real-world problem. So let's jump into it. The distance a car is from an observer measured in meters is given by the function, by a function of time given in seconds by this function named d. So it's a cubic function. I know it's going to have in behavior like this. It's a polynomial. It's going to exist everywhere. It's going to be nice and smooth. I might turn around. I'm allowed 2 turns, or I might just look like that. Let's try to graph this distance function. So I'm going to open up the xy plane. I'm going to put time down there and distance here. I'm also, because we're going to concern ourselves with the derivative, I'm going to plot the derivative as well. So the rate of change of distance per unit time will be velocity, right? That's how fast you move through space per unit time. All right, now this first question here involves no calculus. What is the initial position of the car? That's just us evaluating the distance function when time is equal to 0. And by doing so, we recover that 1. It's measured in meters. So here's our distance function. Initially, when time is equal to 0, we are 1 meter ahead, so positive 1 meter. The second question is where the calculus comes in. What is the velocity of the car after 1 second? So we should find the velocity equation, the derivative of the distance function, and then we should evaluate that function at time is equal to 1. By differentiating this distance function, we get t squared minus 8t plus 12. And by evaluating the velocity function at time is equal to 1, we get 5 meters per second. All right, so initially, or sorry, not initially, when time is equal to 1, so somewhere over here, we are traveling forward at a rate of 5 meters per second. So we're increasing our distance away from the car, or away from the observer, at a rate of 5 meters per second. But I don't know if I'm here or down there. So let's evaluate the position at that time value as well. So even though the problem doesn't request it, if you evaluate your distance function at 1 second, you get 28 thirds of a meter, or 9.3 repeating meters. So somewhere over here at 9.3. So that cubic function, it's going to exist down here. It's going to have that same in behavior, but we don't care about it because we don't look at negative time values. The important part is initially we're at 1, and then we travel forward at a rate of 5 meters per second when time is equal to 1. All right, let's keep going. What's the velocity of the car after 4 seconds? We evaluate inside of our velocity function, time is equal to 4, and we get minus 4 meters per second. So over here, when time is equal to 4, we are traveling backwards. So apparently we turn around sometime between 1 second and 4 seconds. If we evaluated our distance there, so again, the problem doesn't ask us to do this, but just for completeness, if we evaluate the distance function at 4, we find that we are 19 thirds of a meter away, or 6.3 repeating meters. So right here, we're at 6.3 meters. All right, second to last part. What is the velocity of the car after 7 seconds? We evaluate the velocity at 7 seconds, and we get 5 meters per second. So a positive velocity. So over here at 7, we're traveling back away. We're increasing at a rate of 5 meters per second. So apparently that cubic function actually does turn around twice. Somewhere between time is equal to 1 and time is equal to 4, and somewhere again between time is equal to 4 and time is equal to 7. In fact, we can figure out where those points are. So When does the car change direction? What time values do these turns happen at? Well, they are when you change your velocity, right? Where you go from increasing to decreasing, or from decreasing to increasing. So if we were to plot the velocity function as a function of time, notice your velocity function is right there. It is a second-degree polynomial with a leading coefficient that is positive. So it's going to be concave up. And it does actually enjoy two roots at time is equal to 2 and at time is equal to 7. If you were to factor that equation, you would get t minus 2 times t minus, oh, sorry, not 7, 6. So let's analyze these graphs. I'm going to switch to purple for the final conclusion. We start at an initial position of 1, and we increase our position away from the observer, so we're traveling away from the car as we experience positive velocity. But our velocity is getting smaller and smaller until it hits 0 at time is equal to 2. That's this time value. Then we turn around and we start to come back towards the car. So we experience negative velocity. And we keep traveling back towards, or sorry, not back towards the car, back towards the observer. And we keep traveling back towards the observer until time is equal to 6. And at time is equal to 6, we start to experience positive velocity again, or said another way, we travel away from the observer.